Now we're going to apply and state the second of Kirchoff's circuit laws, and that is based on the principle of conservation of energy. And here I abbreviated KVL, or Kirchoff voltage law, stating that the algebraic sum of all the voltages around the loop is 0. And we note here, I labeled it properly, so that's the first thing you need to do is assign the reference marks, the polarities, and be consistent with the passive sign convention. Say the direction of the current is this way, then this must be plus for V1 and this must be minus, so these are my reference marks. And that's how we're going to write our KVL based on these reference marks, independent of what the device is. So here we have note that when we go from a plus to a minus, when we write the loop equation, that this is known as a voltage drop, and then when we go from a negative to a positive, the voltage is negative, and that's known as a voltage rise. So here, loop 1, I'm going to label it right here, that's loop 1, and we're going to go through V1, V2, and V3. For loop 2, we're going to go through V3, V4, and V5. And then we have another loop, let me put it in blue, which is really the outside part of the circuit. And we'll call that loop 3. And we'll see that loop 3 can be generated from loop 1 and loop 2. But this can be used to help verify that our calculations are correct. So let's write the KVL equations for loop 1. So again, we'll start off here and we should end up here, and that's equal to 0. So we're going from a minus to a plus, so that's a negative V1. We're going from a plus to a minus, so that's a plus V2. So we're entering that device with a positive. And then here we're entering V3 with a positive, so that's a positive V3, and that's equal to 0. For loop 2, we're going to start right here, and so we're going from negative to positive, so that's a negative V3. Then we're entering a positive V4 and entering a positive V5, and that's equal to 0. Finally, for loop 3, we'll going through device 1, 2, 4, and 5. So here, this would be a negative V1. We're entering a positive V2 and a positive V4 and a positive V5, and that's all equal to 0. And that's it associated with writing the KVL. And what we're going to do next is assign some numbers in terms of what we're given in certain voltages, polarities associated with some devices, and then find the polarities associated with devices that needs to be found. Okay, now we assign some values of V1, V2, and V4 respectively. So we're here for V1 we're assigning a plus 5 volts. For V2 we're assigning a minus 3 volts. And for V4 we're assigning a plus 10 volts. And we're asked to find V3 and V5. So here what we're going to do is going through loop 1. Notice we have assigned two types of signs. One sign associated with writing the KVL, and signs associated with the actual voltage polarities assigned to these circuit variables. So for here we have a minus, and then inside here, the parentheses here, we're going to put a plus 5 volts. That's the actual polarity of V1. For V2 we put a plus minus 3 volts. And then what we're trying to find is V3, and that implies that, and this is all equal to 0, and that implies that V3 is equal to plus 8 volts. So that's our first answer. And then we can apply loop 2, but we know what's V3, so that's a minus plus 8 volts. For V4, it's a plus 10 volts. And then for V5 is what we're trying to find. And you can see here for V5 that implies that we have minus 8 plus 10 is a plus 2, and then putting it in the other side means it's a minus 2 volts. So that's what we're given. Okay, so we already found our unknown variables of V3 and V5. Now let's just take a look at loop 3 and see if it's consistent. In fact, when we do generate the loop 3 voltage equations, it can be generated from loop 1 and loop 2, so we really didn't need loop 3. So here for V1 we were given as plus 5, so there's a negative plus 5 volts. V2 is a plus minus 3 volts, and a plus for V4 is a plus 10 volts. And then for V5 we found it was a plus negative 2 volts. Okay, is equal to 0. So here we have minus 5, minus 3 is minus 8, and here we have minus 2, which is minus 10, which adds with the 10 volts of V4, and that's equal to 0. So this checks out. So we're consistent in that respect. One thing we should note that when we have n nodes and E2 terminal elements, then there are only E minus n plus 1 independent KVL connection equations. So in this case, our number of elements is 1, 2, 3, 4, 5. So E, our number of elements, is 5. The number of nodes is 1, 2, 3, and 4. So we subtract 4, and then we add 1, and then we need only 2 KVL equations. Okay, again, E is the number of elements, which is 5, and so our generic formula would be E number of elements minus n plus 1 is equal to the number of KVL equations, and in this case it's 2.